Hello and welcome to the second part of Lecture 24. Here we're going to cover Section 10.6, and the topic we're going to cover is conservation of angular momentum. This is going to be built on the ideas that we saw in the previous lecture that defined angular momentum. In particular, we're going to see a lot of the definition of angular momentum of a solid object, which was I omega, where I was the moment of inertia and omega was the angular velocity of that solid object. That's going to be the primary way that we look at angular momentum. And we're interested in its conservation, the fact that angular momentum, like momentum, is conserved whenever the sum of external torques on the system, whose angular momentum we're measuring, is zero, right? So as long as there's no net torque, then the system has angular momentum that remains constant. It remains at some constant value, units of joule seconds, but that angular momentum is unchanging. And just like with conservation of momentum, this is going to be applied to situations where a sum of external forces, and now torques instead, because forces acting at some distance from an axis, okay? There's always going to be some relevant axis of rotation. But importantly, that there's conditions where that idea of external forces, external torques, being zero makes sense. It could be something that happens quickly, something where there really is no forces around, like in a vacuum, okay? But collisions, explosions, those would be good examples, and we're going to continue to see that, just like we saw with translational momentum, but here it's systems that rotate, okay? Just like with conservation of momentum, we're going to think about conditions where things stick together after colliding or break apart, or maybe something was together as a whole and broke apart, or something changed. And in changing in some way internally, the momentum is going to change, okay? But the important thing is every time we see these problems involving angular momentum, I'll say the majority of the time, really L equaling I omega is going to be the primary tool. That's going to be the equation that we're going to be seeing over and over again, okay? Of course, we'll see that in practice in just a second, because we have our first example coming up, okay? And it's important that this conservation of angular momentum is occurring as a vector, okay? So the directionality matters, usually just getting flipped one way. So either we have an angular momentum that's positive that might point up, and an angular momentum that's negative and would point down if positive was defined as up, okay? And these are the same sort of vectors that we've been seeing all throughout the rotation chapters. These are vectors that are perpendicular to the plane of rotation, right? I spoke about that in the last lecture, but it's good to remind ourselves that angular momentum, just like angular velocity, just like angular acceleration, just like torque, these are all vectors that point perpendicular to the plane of rotation, all right? Let's get to it. Let's look at the first example. So this first example I chose to be the first one because it's simple numerically. It's simple to solve. There's not a complex algebra or trigonometry involved in the solution, let alone calculus. But conceptually, it's a little strange. It is the kind of effect, the kind of motion that we don't expect. We don't really have a good physical intuition for whatever reason. It's not something we experience in everyday lives, in my opinion. I think that's why we don't. And so the effect is almost, it seems to be motion for nothing, motion out of nowhere, right? It doesn't seem to quite make sense at first pass. Obviously, there's an explanation. It falls into the same category as gyroscopic motion. And I'll briefly talk about gyroscopes in the third part of this lecture, a very brief lecture. But a gyroscope, it almost seems like that it starts to rotate for no reason, because you just drop it. You let a gyroscope start to fall, and then it starts to spin the opposite way that it would normally fall, right? And again, more on that later. So, okay, why do I say that? Why do I say that this example has that type of unexplainable motion? Well, let's take a look. So a person sits on a chair holding a bicycle wheel with a moment of inertia about its central axis of rotation, okay? So here is our bicycle wheel, okay? It's rotating like so. So I want you to all to take your hand, your right hand, importantly, and curl your fingers in the direction that you see that pink arrow rotating, right? So kind of curl them so that they're curling in the counterclockwise direction, all right? And then noticing that your thumb points up. Well, that's the direction of angular momentum. That's also the direction of angular velocity, but angular momentum is always equal in direction to angular velocity. Just recall that L equals I omega. And so when you look at that equation, you see that, well, they have to be parallel to one another. Okay? So that's our angular momentum of a bicycle wheel. The person's at rest. Okay? They're not moving at all. But they're sitting on the chair that can rotate. So the person with wheel has their own moment of inertia. Okay? IB, okay? And that is 8.1, okay, kilograms square meters. Obviously, units of moment of inertia, just like the wheel is 1.1. So the person has a much bigger moment of inertia. They're much more massive. The radius of rotation is probably a little bit bigger. Okay, they're not a simple shape, but these are just estimates of their moments of inertia. Okay, and that's about a central axis of rotation with the chair. Okay, now we're not the fact that the axes are offset from one another. We're not going to worry about that. It could add a detail to the problem. Essentially, it would change the moment of inertia of the person, because now the person is holding a wheel that would kind of act like a particle of sorts. That's a tethered particle that's rotating at whatever distance it is between these two axes. But think of the moment of inertia here of the person with wheel as being the total moment of inertia. So it includes the fact that the wheel is not exactly aligned. It's not like the person's holding the wheel over their head. That might be a simpler example in a sense if we were trying to build this problem from the ground up. Okay? But here's the thing. When the person flips the wheel over, and I give you the angular velocity of the wheel, okay, we're going to use that to calculate it. When the person flips the wheel over, they're going to start rotating. The person that was previously at rest. And they're going to start rotating in the direction that the wheel was spinning in. Because you think about it, that wheel that was spinning in the counterclockwise direction, being held by the person, when the person then grabs the handles of the wheel, you want to imagine this wheel kind of having handles on either end that you can easily hold, easily grapple, that when the person flips the wheel upside down, now the angular momentum vector of that wheel is pointing down. Okay? We see it. It's pointing down. It was pointing up. And then we can confirm that with our right hand, because if we now take our fingers and rotate in the direction of the flipped wheel, they'd rotate clockwise, which would force the thumb on our right hand to point down. That's the new direction of angular momentum. But the angular momentum must be conserved. It's got to be. And that means that the person, okay, has to start rotating in the counterclockwise direction, because they now need to add an angular momentum vector to the system. Okay? The system has no external torques, right? And so they need to add an angular momentum vector to compensate for the change, because we need the total. We need L initial, total L initial to equal total L final. And think about it. This tall upward vector plus this shorter, half as short, or half as tall, half the length, downward vector, when we put those together, the effect we get is exactly what the original vector was, right? So you see, it makes sense mathematically. We're conserving it. But it is an odd result, isn't it? It's an odd result that the person just starts to spin from nowhere. They were just at rest. Just flipping a wheel upside down makes you start spinning? Well, yeah, it does, right? Which is pretty amazing. Okay, so let's now run through the solution. So the whole concept, the great starting point to really any of these conservation problems is write this out, all right? Just remind yourself that that's how you start every one of these. Okay, then we're going to think about what actually composes L initial. So this is all about solid objects here. Okay, rotating about a fixed axis. So we got I wheel times omega wheel. We've got I for person with wheel times their omega, which we're trying to find, okay? And then we've got I wheel negative omega, okay? And omega is the one that's given. It's our 2.4. Why negative? Well, because the wheel didn't slow down at all when we flipped it, right? It may drag in the real world might make it slow down. But here, flipping it upside down, it's going to keep spinning at the same rate, just in the opposite direction, okay? All right, so this is our conservation, our initial and our final angular momentums, equal to each other, okay? All right, so then it's just a matter of solving for omega b. That's our unknown. So you can see it's the only one that I left as a variable. So we're going to solve for. I already plugged in all the numbers a little preemptively here, okay? And then I'll go ahead and show the symbolic expression. So if I was just to solve for omega b from this equation up here, I get something that looks like that. All right, so you can see, cleans up a bit. And so then we get this answer right here. All right, why is that? Well, because this is just L times the angular momentum of the wheel. So what I'm seeing then is that my angular velocity of my person holding the wheel is going to be equal to twice the original angular momentum. Well, that makes sense, right? Because it's just twice as tall. And then, since I'm asking for velocity, I have to divide by the moment of inertia. And that does mean that the person, although they have twice the angular momentum, right? You can see its magnitude, twice as big as the wheel. They're not going to be spinning faster than the wheel. That would not make sense, right? That would definitely fly in the face of what we really know to be physically possible. And that's because they're more massive, right? So they're much greater mass, they're much greater inertia, means that they will start spinning at a much slower rate, even though their angular momentum is twice the size. Okay? Plug in the numbers, and we get 6.52 radians per second. And that's in comparison to the 24, right? So you can see it's significantly smaller. But, they do have a moment of inertia that's 8 times bigger. So, come on. All right. So, all makes sense. You see the approach, right? Really neat, really neat demonstration. Okay. All right. So let's look at some other examples, kind of fall into other categories. So one thing that doesn't translate well from, and I always say translate, but now I'm going to say translational, right? So that doesn't really go well from ideas from translational motion over to ideas of rotational motion is this next type of angular momentum conservation, because it's kind of a typical type of problem. And I would group this type of problem, and I'd call it the ice skater problem, because the idea that we all know from figure skating is that if an ice skater is spinning with their arms outstretched, well, now they're an object, right? Their object has, in general, a moment of inertia that is proportional to the radius squared. So having their arms out, even though their arms aren't particularly massive, really significantly affects their moment of inertia. It makes them have a much larger moment of inertia. And so when they pull their arms in, they reduce their moment of inertia, which means something's going to have to compensate for that change because they don't have any external torques acting on them. Their system, their body as a whole, represents a perfect example of conservation of angular momentum. So when they pull their arms in, their moment of inertia has changed. Angular momentum is equal to I omega. So what's going to have to change to compensate for the change in I, right? Omega. And it's got to go up because I went down. They start spinning faster, right? We all know this. Okay, so there's no real equivalent to that in translation. It's this neat effect about why rotational physics is honestly more interesting because it's got these extra intricacies to it. So that's the problem. But in this case, instead of an ice skater, it's a giant cloud of interstellar dust. Okay? But what's going to happen is that big cloud with its outstretched arms is going to crunch in on itself, become much smaller, become a star, and in doing so, the star will be spinning quickly because the cloud was initially slowly rotating. Giant cloud, many light years across, right? Is slowly turning. But when it crunches down to a star, okay, just a few million miles across, okay, or let's see, so if we have 6,000 kilometers, I'm just thinking about the radius of the Earth and then the Sun, so I should say, like a tens of thousands of kilometers across, okay? So it's going to be spinning much faster, okay? It's the ice skater, but at a more dramatic scale. Okay, so let's run through the problem. Okay, so we've got a interstellar cloud. It has 20 solar masses of energy, not energy, but unless we're converting the energy, the mass to energy, but it's got 20 solar masses is its mass. Okay, so it's 20 times the mass of the sun, and the mass of the sun is 9.989 times 10 to the 30 kilograms. Okay, so that's how many kilograms the cloud has. All right, so it's going to collapse under the force of gravity if the cloud starts off as a sphere with uniform density of 3 times 10 to the negative 9 kilograms per cubic meter. It's a very, very low density cloud, as interstellar clouds are. And it condenses to a spherical protostar with a uniform density of 1410. So that's pretty fascinating. That's kind of actually typical of protostars when I looked it up. That's about 1.4 times as dense as water. Okay, stars aren't particularly dense. Okay, at least not there on average. Okay, their density does vary with depth. Okay, so but that's there. In this case, it's a uniform density for whatever idealization in the problem. Okay, and the initial angular velocity of the cloud is 1 revolution every 1,000 years. Okay, and that's a little fast, right? That's probably the cloud would be moving much slower than that, and that makes our number actually a little bit more dramatic than it would be. But for whatever reason, this is a quick cloud. It is in a tumultuous section of the galaxy. Okay, so the final question then is, what is the translational velocity of a point on the equator of the protostar? Right? So if there's one little pocket of gas spinning around the equator of this protostar, where the velocity would be fastest, right? Because the poles are at rest. It is a spherical object just like Earth, right? And then how fast would it be going, right? What are we talking about here in terms of centripetal effects? All right. So let's do the problem. Okay. So we're going to use this formula for the volumes, and we need that because we're given a density. So it's important to relate things with volumes. It's just the volume of a sphere, 4/3 pi r cubed. Here it is. Here we've got L initial equals L final, the way we start out every one of the problems. But this one, it's not even, I didn't draw the vector notation, right? It's just L as a scalar equals L final as a scalar, because there's no directionality here. We won't have to worry about the vector, okay? All right, and what is that going to look like? Well, we know that they're both spheres, so they're both going to have moments of inertia of 2/5 mr squared, okay? And that's just the initial radius and the final radius. The mass cancels because it's the same mass, all right? And then we'll come back to the mass in a minute. And then we've got our initial angular velocity, which we'd find from that information there about its period, because we can relate its period to angular velocity very easily, right? You'll see. And then our final angular velocity, which we can just solve for. And then ultimately, since we were asked for the translational velocity of a point along the equator, we'll just use V equals omega r to finish things off. And that will be RF. All right? So an important step is to think about what's going on with the radius, because we have enough information to find the radius, okay? So what we do is we just write that mass is volume times density, okay? So in this case, it would be volume of a sphere times the density, okay? And we were given both the densities. So then I just set up and solve for the initial radius and the final radius, okay? Just from that equation. Because we know it's the same mass, there's no loss of mass throughout it. And so then this is what we get for the initial radius, is what we get for the final radius. Okay, so 2.57 times 10 to the 9 meters, and 1.99 times 10 to the 13 meters. Okay, so huge change in density, and in terms of the size, actually not. I'm drawing a blank on how many meters there are in a light year, the order of magnitude wise. But I won't go off a tangent. But anyway, so very large gas, but also, fairly large star here, right? It's 10,000 times smaller. Anyway, so now we'll simply solve for the angular velocity, the final angular velocity, because we know the initial angular velocity. How do we know it? Well, we simply know that it is 6.05 times 10 to the 7, and that's revolutions per 1,000 years, okay? And let's see, if I do that, radians per minute. Let me just make sure. Okay, so I think here this number is just coming out of this ratio. It's just coming from taking this, squaring it, and dividing by that, and squaring it. And then plugging in the initial angular velocity. Yeah, and I just left it in the units that I was given as. So I just left it in revolutions per 1,000 years, okay? And then I'm just going to convert that over to radians per minute, because I know that every revolution is 2 pi radians, and then I know exactly how many minutes are in a year, okay? And then, right, and I leave it in that unit, not particularly remembering why I did, but you can also just write in the more traditional radians per second, and it's 1.2 times 10 to the negative 2 radians per second, okay? That's the final angular velocity. That's not huge, right? But we wouldn't expect it to be too huge, because we're talking about a huge, massive object, and the bigger an object is, the slower it's going to have to turn, and not create, well, relativistic effects, right? A surface that's too fast, approaching the speed of light. And then it can't, overcome forces, right? If things spin too fast, they're going to pull themselves apart, no matter how strong a force we're talking about, of the 4 fundamental forces of the universe, right? There's limits. Okay, but let's finally solve for that translational velocity we're asked for. So we were asked for the translational velocity on the equator. So then I just take that omega f in radians per second, so that one there, and then multiply it by RF, which I know to be 2.57 times 10 to the 9, and there we go. There we get our velocity along the surface of our star. And now, I just mentioned relativistic effects. This is pretty darn fast, right? This is exactly 1/100th the speed of light. Not enough to have significant relativistic effects, but also faster than your average star surface. It does kind of beg the question, is that possible? Can you have stars that spin that fast? Yes, to some extent. I think that there are very fast stars other than neutron stars. And sometimes that can have a big effect on how the solar system is shaped. I mean, big theory about our solar system is that we have much less, or we had much less gas between the planets, which is why we don't, our particular kind of layout of having the gas giants only in the middle and no gas giants close to the sun. And that's probably because we had a very fast star, 4 billion years ago, quickly rotating, all right? Because that creates a big magnetic field and other effects, okay? Cool. All right, so that's our ice skater example, but with interstellar stars, or interstellar clouds and the resulting stars. I'm going to leave example 3 for you. So example 3 is a collision. It's the first collision that we're going to see. I'm leaving it for your practice because it's a good example of dealing with a collision, similar to some homework problems I assigned you, or at least one. And the idea is that you have some rotating object, and you got a translating object. And when the translating object crashes into the rotating object, at the moment of collision, itself, the thing that was translating, is effectively rotating relative to the axis of rotation of the thing it just crashed into, right? Because of course it is. It's crashed now. So it's like you crash an asteroid into the surface of a planet. Now it's going to be turning. What's left of the asteroid is going to be turning with the planet, and so then we can think about the overall effect. Okay, but don't worry. I will show you an example of a rotating thing crashing into a non-rotating thing in just a minute. But first, let's cover the other kind of key grouping, other major grouping of angular momentum types of problems, and that is two rotating objects crashing together, because that seems like an obvious choice, okay? So in this case, we have a spinning turntable, and we know its mass, and we know its initial angular velocity, okay? And then a uniform density rod is dropped on top of it, okay? Now the rod, I guess, was typically, also you could maybe, was the rod really spinning? Like here, the rod is not spinning, but it also could have been, right? You could imagine dropping it and kind of giving it a twist as you drop it. But in this case, we're going to drop it straight down. But it's coming down on the same axis as the turntable, okay? So like as I say, it lines up with the center. And I'll show you a picture of it. It sticks upon contact, so this would definitely be an inelastic collision, okay? So definitely a loss of mechanical energy is necessary. Both objects have diameter or length equal to 2 meters. It's diameter or length because it's, in the case of the rod, it's length. In the case of the disk, it's diameter. What is the final angular velocity of this new combined object, and how much energy is lost? So here's the picture, right? So we've got our spinning plate, our spinning turntable, and we're dropping the rod straight down on it. Okay, and again, I would consider this a collision between two rotating objects colliding on their respective axes of rotation. It just so happens that the rod is not rotating to make the problem, I guess, as a good simple introduction. All right, so here we have the moment of inertia of the turntable, that of a cylinder or a disk, and here we have the final total moment of inertia, which is the sum of our cylinder one and our rod rotated about its center. Because remember, a rod rotated about the end is 1/3, and 1/3 ml squared, and a rod rotated about its center is 1/12, because it's easier to rotate. Okay, we're going to start the way we do every time. L equals L final, or L initial equals L final. Here I'm using the notation of L and L prime. L prime playing the role of L final. I times omega, that's our L initial. L final, I times omega. What's changed? Well, I, right? It went from I just turntable to I of the turntable and rod together. And angular velocity thus must also change. Is it going to go up or down? Well, it's going to go down because all we're doing is just making I bigger, effectively. All right? So it's just going to be that much smaller than omega. Okay? So as we continue on, then we see really what we have here is just the initial angular momentum divided by that the initial moment of inertia divided by our new larger total moment of inertia. Okay, so there we have it. We have its final angular velocity. Is it slower? Yeah, it went from 19 to 16.5. It decreased. Okay, we just kind of added inertia to the system. Now I also asked for how much energy is lost. Well, we can simply do that by just thinking about the initial state when just the turntable was turning, and we know its moment of inertia, we know its initial angular velocity, and now we know the final angular velocity, so we just do this expression for k final for the system as a whole, but with added rod, and so we just plug in all our numbers, and we end up with, right here they are plugged in, we end up with 289 joules. So quite a bit of mechanical energy. And because that's all the energy that went to, allowing these things to stick together, like all the effect that had to take place, right? The compression, all that, that's all that is all lost energy. Okay? Mechanical energy at least. It changed to some other form, heat, sound, and so on. Okay, so example 5 is a more complex version of example 3, that's rotating object being collided with or colliding with a non-rotating object. It's definitely kind of a key type of problem. You have a homework problem like this, and it's rather complex. It's a good one for practice. I'll post a solution to it so if you feel like you can't get it worked out. But it's not the one I want to show you today. It's one I do typically show, but I instead want to show you what I assigned as a post quiz previous semesters that didn't fit into this semester. And same sort of idea, okay? And also very similar to 1/3 of the lab that I posted. So if you look at the most recent lab 11, you'll see that there's this great simulation that you can work around with. And one of the questions is based on something just like this. It's basically a bullet colliding with a board, getting stuck into it. And actually, to make it more like the lab, I went back to having the pellet becoming embedded in the board, which is the way I've asked the question before, instead of making it more complex and having it bounce off. So it's, again, an inelastic collision. I was tempted to make an elastic collision with the bullet bouncing off. But the issue there is, do I want to make it partially inelastic or fully, or fully, partially elastic / partially inelastic, or do I want to make it fully or perfectly elastic? If I make it perfectly elastic, that's fine. We could have used conservation of energy to find the recoil speed of the bullet, but it's just kind of an extra step. I was tempted to do it because we don't have any examples currently that show a good inelastic collision, but there are some I cited in the homework, so at least you have that. But anyway, let's get to the problem. I'm just going to run through it quickly so we can wrap up this video. All right, so we use conservation of angular momentum to find omega final after the fully inelastic collision between the bullet and the board, okay? So we're just going to use L initial equals L final. There's no external torques. It's a perfect system for conservation of momentum. All right, and then so we can see one thing we have to do is we have to kind of go back to this definition of angular momentum as a cross product. And we have to do that for the bullet only, because the bullet isn't the perfect candidate for I times omega. It's not a rigid object with a fixed axis of rotation. It's behaving, like a rotating object upon collision, because it will rotate with the board. But we really have to think of it as translating at that moment, but relative to another axis. And like you saw in the previous lecture, anything translating relative to an axis effectively has angular momentum, and also has torque for that matter, okay? At least if it's accelerating. Okay, so that's the idea, and that means that the form that the angular momentum of the pellet, so I guess I call it a pellet, not a bullet, but the angular momentum of the pellet's going to take is this, okay? Now, that's actually just the angular momentum of a tethered particle, right? Because we think, I omega for a tethered particle would be mr squared times omega, okay? And so we look here, we've got that, that sort of form for this expression. But instead of it being, I omega equals, I omega equals mr squared times omega, then it is mr squared v over r, which means a couple of the r's cancel, and then we just have mrv. Well, there it is. M, mass of the pellet, v, and then r, which is the length or the distance, I should say, from the axis of rotation to the point of collision. That's our moment arm, okay? All right, so anyway, so there it is, okay? Why cosine phi? Because the bullet isn't coming directly in. The bullet isn't coming perpendicular, and so the cross product has a component that needs to be taken, okay? We're only interested in the perpendicular component, v perpendicular, that's actually going to show up in the angular momentum, all right? So that's it. That's the idea, okay? That's the initial angular momentum of the system. But afterwards, the whole board starts to rotate, right? It's going to spin up. Yeah, okay, that's what we're going to find. Okay, so our L final is just I total times omega final. That one we can just use the typical formula for a rigid object, and it's going to be I pellet plus I board. All right, what form are those going to take? Well, the pellet is just a tethered particle at that point, truly and really. Okay, the board is the same as a uniform rod. So what? Just 1/3 ml squared. Okay, so we're good there. All right, and we're going to, by consulting the figure, we can see that the pellet, the distance R pellet equals L. That's, like I said, that's its moment arm. And L, the length, the L that's showing up in the moment of inertia of the board, is just twice that, because the pellet collision is happening exactly in the middle, which is nice, actually, because then we don't have to recalculate the center of mass, which you'll see in just a second. Okay, so then we can find our expression for our final angular momentum, the total moment of inertia times omega final. Okay, so then we can just set these two equal to each other, the initial and final angular momentums, okay, and then solve for our only unknown, which is this one right here, omega final of the combined system, board with embedded pellet. And we get 15 radians per second, okay? So that's how fast it's going to start spinning immediately after the collision. And this was a collision where there was no external torques during the collision, right? This was a perfect example of conservation of angular momentum, all right? Could we have done it with translational momentum? After all, by 1/2 of the system was translating, right? It kind of seems like maybe one we can solve both ways. No, because this isn't two particles colliding. This is a particle colliding with an object. So we have to use angular momentum, right? And so the angular momentum is the bigger conservation law, because it allows us to include translational aspects, whereas if we just wanted to use translational momentum, we couldn't include rotating objects. Wrong way. All right. So here we have conservation of energy. So we're going to use using conservation of mechanical energy, we can find the center of mass or the height of the center of mass. Okay, so HCOM is the maximum height reached by the board pellet after collision. It's this distance right here. Okay, here I call it H. I should have labeled it as HCOM, but this is exactly what HCOM is referring to. It's the height from the center, the COM, initially to the final location of the COM. Right? That's how high that point's going to swing out. Okay, so we just set that up with just conservation of energy. What form is it going to take? Well, the system immediately after collision is entirely a kinetic system. It doesn't have any potential. So it starts with all rotational kinetic energy. Yes, rotational. Okay, no translational energy. It's not a rolling system. And then afterwards, it's going to be entirely gravitational potential energy. But remember that you can only apply that idea if you're finding the gravitational potential energy of the center of mass of the system. So that's why it's very important that H here is HCOM. Because if I was looking for the height of, say, the tip, well, that'd be a very different value, right? The tip went that far. That would give me a different amount of energy, and it would be wrong. You can only do it for the center of mass. Okay. So then we find out how high the center of mass is, and we've answered the question, right? Because part B was, what maximum height does the center of mass reach? Good. All right, which happens to also be the geometric center, because everything's aligned, it's a uniform rod, the bullet hit, or the pellet hit exactly in the middle. Okay. Part C asks for how much energy is lost. I think one of the best ways to find this is just to find the initial kinetic energy of the pellet, because that was all the energy initially, and then subtract the final potential energy of the board with embedded pellet. Okay, because we know HCOM, right? So rather straightforward, just plug in the numbers, many of which we already have. The only one that's calculated one is the HCOM. Okay, and there we go, 9.1 joules. That's how much energy was lost. Not too much, because I guess it just actually wasn't that much energy in the system. In terms of the total amount of energy, I think it should be pretty high, because it was a small thing hitting a big board. So I think proportionally, for the percentage, I didn't calculate it, but the percentage actually would be quite high about the amount of energy that was lost. Okay, so I hope some of you stuck with it, with this video, and saw all these important examples of angular momentum conservation. All right, well, thank you for watching, and please check out the third and final part of this lecture, where I just briefly discuss gyroscopic motion.